before the break, and I hope to make the last 15 minutes as interesting as possible. We already had some really nice presentations so far where we talked about how we can use quantum science and information theory. We can like chill with some cool states of matter with quantum science, and we also use quantum science in quantum gravity and space-time. So I'm going to take a completely different approach here, which is that we're going to go deep underground and into a nickel mine in northern Ontario and trying to see how we can do some quantum science experiments over there. So this whole presentation is kind of coming a full circle here. We started the day with a question, what is quantum? So maybe I can ask this question again. So based on all the things that you learned so far, does everybody wants to like make a guess on what is quantum? Anyone has any new insights? I had heard last time that it was like a buzzword. So since I am on a timer, I'm going to keep moving ahead here, is that quantum is a rule book for anything that's microscopic in nature. So over there, we kind of deviate from a classical mechanics and start talking in terms of discrete quantities. So for example, like energy is no longer just a continuous spectrum. We talk in terms of discrete steps or energy levels of energy levels. There are also certain terminology that comes in, like uncertainty principle, superposition, and you heard a lot about entanglement. So basically, if this were classical mechanics, I'd say, hi, I am Vijay, and I am standing right here on this T. But if this is, if I talk in terms of quantum mechanics, I'll probably say, there's a 99% probability that I am Vijay, and I'm standing somewhere here in this region. And you also spoke a little bit about how quantum science is has enabled a lot of technologies right at the beginning of our session today, all the way from nuclear reactors to LEDs. So taking a segue to the next slide, which is that quantum science finds its way to all the different subjects that you have learned through your high school as well as your undergrad courses. There are also a lot of applications. We have gone through quite a few of them, sensors in our keynote talk. We also went through communications and some materials. What I'm going to be focusing today on is quantum computing. So when we talk about computing, let's talk about the language, right? The language that we use in computing, it's binary. That is, it's either a 0 or a 1. Now, the classical computers, we talk in terms of bits. Each bit is basically just a transistor. If the transistor is on, you have a 1. If it's off, that is, there is no current flowing through it, it's a 0. Now, what happens in quantum mechanics is that you can use anything that's in a microscopic but isolated state. Like you can talk in terms of superconducting circuits or currents. You can talk in terms of a trapped ion or photons, such that if light is oscillating in a vertical plane, you can call it as a 1. If it's in a horizontal plane, you can call it as a 0. And there is also a superposition of states. So I have an animation here which I've got going on there, which is that if you have a coin that's flipping, it's in a when it's in the air, it's kind of in a superposition of two states, 0 or 1. It's only every time you look at it that you get it as either a 0 or a 1. But there's always like a probability associated with this, that each time you look at it, it could either be a 0 or a 1, and the next time you look at it, you're like, what's the chance it could be like 2 zeros in a row? Then what's the probability it can be like 2 zeros and then a 1? So for each outcome, there is a probability associated with it, and that's how quantum bits are different from classical bits. You can use your classical computers for everyday programming and playing games, but where quantum computing comes in handy is more like cryptography, figuring out different new novel materials, and training large language models, and so on. So you have this special phenomenon like entanglement and superposition, which can be used in designing quantum computers, which you cannot use in classical computers. So what are the challenges in controlling a quantum bit? What I've shown you here is like a superconducting quantum bit or qubit, also known as a transmon. It would look very much similar to any of your Intel or Ryzen chips that you see. It's like a silicon chip, and you can see like all these silvery surfaces here. Each of them is a qubit. So there are like 5 qubits on this chip right here. Now, each of these chips, they have a qubit, and those qubits have got some energy levels, which was spoken about briefly in a previous talk. You can choose like the ground state of its energy level as a 0, and if you give it some excitation, it will go to a higher state, and you can call that as your 1. So now you have your language established. You have a 0 and a 1, which you use for binary. And if your qubit is in the ground state, you can say that, okay, I'm transmitting zeros. If you excite it, you give it a 1. Now, how do you do that? Is that you see all these feed lines here, these connectors in between. You send microwave frequency through it. The frequency has got some energy, so that's how you kind of excite everything and send it to a higher state. So that's our way of controlling a qubit. But then comes the challenge of being able to control it in a way that we want it to. What happens is that, or what has been studied in the past, is that radiation can often come in the way of us being able to control and hold a qubit steady in a particular state. There is radiation all around us. There is radiation that is being emitted by you. If you eat a banana, there's potassium-40 coming from it. There is a lot of radiation that's coming literally from your bones right now. So all of those radiation keep on falling on everything around you, including the chip that we have here. And these qubits are extremely fragile. Let me go on to the next slide where I try to explain this a little bit more. On the surface, the chip looks really nice, right? But if you look at it with a microscope, you will see that it has got a lot of bonds. Each crystal has got a lot of bonds. Now, some of those bonds can be broken and can be dangling. Furthermore, if you have any kind of radiation passing through those chips, they can actually break some of the bonds, and they can create more dangling bonds. Now, when those bonds are kind of oscillating on its own, you can see like two different bonds here, atoms which are oscillating at its own frequency and kind of vibing with each other. They create their own frequency. Now, 2 slides ago, I said that we control our qubits as well with some frequency that we send it, so that we send it to an excited state. What happens here is that now these dangling bonds have their own frequencies, which then start interfering with our way of controlling these qubits. And this is just like one example. There can be like thousands and thousands of such things within your chip somewhere. And all of them will affect the way we control our qubits. So in isolation, we had the theory right, but in reality, what happens is all of these factors will start affecting how we control our qubits. Have anyone? Oh, yeah. Thank you. That's exactly what I was hoping for. All these traumatic experiences have come back to you, especially sorry for people from the IT. You guys have seen this blue screen of death, right? Right? Especially when you're gaming, that's the most frustrating thing to happen. Yeah. This can happen because of cosmic rays. So cosmic rays are rays that are coming from outer space. They hit the Earth's atmosphere. They create a lot of showers. Now, those particles can sometimes go through your RAM or your processor, and they can flip a bit. What that does is if your computer is kind of sending like a memory location to like the processor and back to the RAM and so on, if it flips a bit, it suddenly sends a wrong memory. And if it sends a wrong memory address, your computer does not know what's happening, and it just suddenly freezes and shuts down. So we know that radiation does affect even your classical computers. So that's why we were more focused in seeing how does it affect quantum computers. Now, if we want to get away from cosmic rays, one way to do that is actually going deep underground. So if you go really deep underground, you can actually reduce it by about 50 million. And just as another fun fact, you guys have heard of northern lights? Those are also from these same cosmic rays. When they kind of interact with the Earth's atmosphere, they create all this plasma, and you get all these fancy lights. So cosmic rays has its own, it looks very pretty, but it can also make life difficult for us. So for our experiment, what we did is we went to a place called Sudbury, that's in Northern Ontario here, and at a lab called Sudbury Neutrino Observatory in Sudbury, as the name suggests. Now that lab is about 2 kilometers underground from the surface of the Earth. So this is one CN tower. So that's about 4 CN towers and a bit more deeper from the surface of the Earth, which is where we go and do this experiment. In fact, I'll be going that again next week to continue on installing my experiment over there. And the lab is actually the size of a big shopping mall, by the way. So let me take you through a journey of like how you get there. That is SNOLAB. That is actually it's an active mine site. They mine nickel and a few other elements over there. So this is SNOLAB. You kind of change into your mining gear here, and you have to make your walk all the way to this head frame here, from where you actually catch a cage to go underground. Because you're going with the miners, you have to be in a full mining gear with all the PPE, that personal protective equipment that you see here. So you gown up all the way. And then, very difficult to see, but we get into something called as a cage with all the miners. And then we go within about 3 minutes or so, you're 2 kilometers underground. That's how fast we go underground. And because of that, there is a change in air pressure by about 20 to 30%. So you guys have experienced this ears popping anytime you go in a flight or some other place. You experience something very similar when you're going in a cage as well, is that you will start having your ears pop, at least the first time when you're going in there, and after that your body gets used to it. And this is something that people take for granted. You don't see sunlight at all once you're down there. Because once you're in the mine, you'll be walking another 1.4 kilometers.
How long do you stay for down there for usually?
For us, one session is about 10 hours, 10 to 12 hours. So it's depending on how they have scheduled it, it's about 10 to 12 hours. We do have food down. We have to take our own food down there, and we also have reserves over there, because I have once been stuck there for more than 18 hours. In a bunker, yes. There are a few stations. So you also sleep down there. Right? So you walk through the mine, and as I was saying, the sunlight, you take it for granted, right? I have had several weeks where I have not seen the sun at all, because I would go underground at 4:30 in the morning. I'll come back up at, say, something like 6 o'clock, and then there is no sun when I go down, no sun when I come up, and for several days in a row, I have not seen a sun. So you reach SNOLAB. This is just outside the lab. Now the whole thing, which is, I said, is as big as a shopping complex. It's actually a clean lab as well. So what does that mean? We have about 2,000 or less particles per cubic feet. 1 cubic feet, just to get an idea, is something like this. This is how big 1 cubic feet is. Normally, if I take a particle counter and walk around here, it will give you somewhere around 1 million particles. In a mine, that's around 10,000 particles. So the entire lab is kept at less than 2,000 particles. That's how clean they keep it. And because of that, they have a lot of rigorous protocols. You go through special showers. Every time you enter it, you have to wear the clothes that they give you. It's almost like being in a sci-fi movie. You have to wear all their hard hats. And then after that, that's actually my experiment site, the water tank that you see in there. That's a low background facility over there. It's called Cryogenic Underground Test Facility, and they have a really nice acronym called CUTE. And that's our experimental site. And in the previous talk, I think Carolina told us about a dilution refrigerator. We have one right inside the tank over there. It's all well shielded, even from the radioactivity that the walls from the mines can create. So what exactly is the experiment? We start with a standard qubit design. We do one surface run. So this project is actually a collaboration between 3 universities. Let me just start with that. Institute for Quantum Computing, Chalmers Institute of Technology, or University of Technology, which is in Sweden, and SNOLAB, which is again in Ontario. Now we start with a qubit design, standard qubit design. We take data on surface here at IQC. Then we take another data underground over there, where we are away from all these cosmic rays and in a well-shielded environment. Then we analyze the data. We analyze the 2 data sets, and we try to see what are the differences that we have between the 2 data sets over here. and we try to make some logical deductions from there on what new fabrication style should we come up with so that we can mitigate the effects of radiation on our qubits and we can control it for longer. We come up with we have a fabrication lab here in IQC as well, or in QNC as well, and Chalmers also makes qubits. So we come up with a new qubit design. We go back up here, we keep repeating until we come to a point where we can actually make some practical quantum processors where we can hold the state of the qubits for long enough for all the algorithms to actually finish processing without too many errors. We mitigate errors, and then hopefully that will be the end of that project. So just as a conclusion, quantum bits are hard to control. There are experiments that actually showed that radiation is a troublemaker for us. We go deep underground to kind of mitigate cosmic rays as well as being a low background environment to try and study the effects of radiation on qubits. And then there is a project which we call as Qt bits, which is going on in a mine in SNOLAB to find better ways of building a quantum processor. So that's kind of my talk, quantum experiments deep underground in SNOLAB, and I am 99% sure this is my last slide. Okay, thank you.
I think we can take just one question before we continue on.
And I'll let John decide.
I think we can do it.
Okay.
How did you get the air so clean with less than 2,000 particles? Like, how did it become so clean?
Right. So firstly, getting air in the mine itself is a challenge. So let me answer from there. We actually have air ducts that go all the way from the surface. It pulls air from another mining site, and then it will bring it down to your lab. And once you're in your lab, we have a lot of filters, air quality filters, and we pass it through the multiple layers of filters, and then you kind of make it less than 2,000 particles per cubic feet. But the bigger challenge is actually maintaining it at that level, because all these pumps and other stuff that you have, they all go through very strict protocols so that they do not end up emitting more particles. So there is a lot of rules and regulations that we have to follow just to maintain it at less than 2,000. And we have actually clean rooms in there, which are class 10, which is less than 10 particles per cubic feet. I think we had another question there.
You mentioned with Chalmers and IQC, you guys think of different qubit concepts. What kind of qubits are you working with? 'Cause I'm thinking like really down, it's really cold, maybe superconducting, but like what do you mean by different concepts? Like what's the difference, I guess?
Right.
Between each
So let me go back to a backup slide which I had, which is, this is kind of like a qubit design which I tried to show here. So this is a qubit that so Chalmers and IQC both have the ability to make their own qubits, okay? There are different types of qubits. The one which I'm talking about is superconducting qubits, all right? So each of these plus shapes that you see, that's a qubit. Now you can come up with different ways in how you place it. Now let's say I place this plus sign here and have this kind of squiggly line going all the way there, and this one all the way here. Now I have fabricated my chip such that the qubits are spaced really far apart. And I can do a study to see, does any data taken with this qubit here affect the second qubit over there? So that's the different kind of fabrication strategies that we can come up with based on the data we have collected. And this fabrication can happen both at IQC or Chalmers. And each of these different iterations that we do, it teaches us something new about how the crystal physics in there, the condensed matter physics, affects your qubits.
Why can't we imitate a very small environment on ground, like a very close environment?
It's very difficult to shield against cosmic rays. Yeah. So those cosmic rays, the only way we can do that is by going underground. Yeah. And yeah, unfortunately. Yes. Yes.
What role does temperature play?
For superconducting qubits, it's the same as the previous talk we talked about, where it was a dilution refrigerator. We hold our qubits at, well, we want it less as something called as a transition temperature of what's the superconducting layer. In this case, it's less than 30 millikelvin is fine for us. The fridge can take us all the way theoretically to about 2 millikelvin or slightly less. Yes. There could be several. So this is a topic that everyone is studying, like Google, IBM. This is a hot topic, which is that my qubit, the bit keeps on flipping, right? Now, as I said, your crystal by default, it has got defects in them, right? If you look under a microscope, it's not as good as it looks from just our naked eye. So those defects automatically ends up creating errors because they exist. They have their own frequency over there. Radiation also plays a role. So this is an active area of research where people are trying to figure out how do I mitigate these errors or how do I minimize these errors. So there are multiple factors. Radiation is one of them.